Okay, we are live. What? Nah. Just fine. Okay, let's get started. So should probably have started earlier so I could get this out of the way. Employee of Columbia University. Columbia University has several grants to develop Stan software. I'm also a co-founder of Stan Group, which provides a lot of things to help businesses use Stan. And according to Columbia University policy, those two things together require such facts be disclosed in presentations such as this. So all that said, for today, we're going to start learning how Bayesians, and hopefully by the end of the day, start to talk about how Stan in particular deals with the situation, which is all too common, where the denominator of Bayes' law is intractable. Like that integral can't be done in closed form, so we have to find a way to not have to do that integral. And the basic way in which this happens is we think about how could we specify some sort of a transition rule to move through the sample space omega. So if we're at like one part of omega now, we go to some other part of omega with certain amounts of probability, such that all the footprints, the places that we land as we're walking through the sample space omega, constitute random draws from the posterior distribution that we specify by specifying just the numerator of Bayes' law. So that's kind of the basic idea, what we're going to be doing today. Also an announcement, this coming Monday, and probably only this coming Monday, I'm going to shift the office hours up into the afternoon a little bit. So they'll be from 3 to 5 this upcoming Monday. Still sign up on Courseworks if you want a slot, and indicate in the comments if you'd prefer to do that online. Like if you can't make it to campus between 3 and 5, but you still want to talk about something, that would be fine. Okay, so just to review again why we need what we're going to be talking about today and also the rest of the semester, we have some posterior distribution for the unknown parameters theta, conditional on y. It can also be conditional on some predictors x, but x is known, so we don't really worry about that. It'll also be conditional on things that you choose to set for your priors, like alpha and beta in the case of a gamma prior or something like that. So we have a posterior distribution for the unknown theta given everything that we do know. That's equal to a prior distribution for theta, which represents in terms of a PDF, often a multivariate PDF. Our beliefs about how what theta is before we see new data, y. So these beliefs about theta can be conditioned on old data that's not being used as part of the analysis. So that's the left-hand part of the numerator. We multiply it by what amounts to a likelihood function. So again, this distinction between a PDF and a likelihood function may seem a little bit arbitrary to you. It's actually pretty important. So before we see the data, f of y given theta is a PDF for y. It integrates to 1 over the sample space of y, all the things that y could be. However, post data, after we've collected the data, we're only interested in evaluating that function for the data that we have. So we're not going to integrate it over y. We're going to evaluate it at one fixed value of y. And if it's considered a likelihood function in the post data case, then we're going to consider this to be a function of theta, proposals for what theta could be. And the integral over theta of the numerator constitutes the denominator, which again is just going to be a single number because we're only interested in evaluating the denominator for the data set that we actually have. Nevertheless, that thing in the denominator, the integral of what's in the numerator over the sample space of theta, is typically impossible to do. The integrals are not just like hard when you first learn calculus. there's a wide class of integrals where we can prove that we can't do them. And that is typically the case. Like I said, theta is often going to be multidimensional, in which case the integral in the denominator is going to be a multidimensional integral. And it's almost impossible that that's going to have a closed form. Even in the unlikely case that we could get the denominator, okay, now we have the posterior PDF. Posterior PDF isn't that useful just by itself. You're probably going to have to do more integrals to get anything useful in terms of inferences or something like that. So say you want the expectation of theta conditional on y. Well, then you need to multiply theta by the PDF for theta given y and integrate over theta. So that's more integrals to do, often multidimensional integrals. And this just quickly gets impossible. It's the main reason why, Bayesian inference only caught on recently, because for, decades and decades, we were pretty much limited to the case where the prior and the likelihood were conjugate. And almost all situations, there's not that many, but all of them that exist, almost all of them that exist, are just for one parameter, models with just one parameter. So, estimating a mean or something like that. And lots of problems in the social sciences necessitate a more complicated model than can be, done with just one parameter and like conjugate relationships. But the posterior PDF is only one way of characterizing a distribution. So, you could use the CDF, but that's actually even harder. What we're going to do is sort of characterize the posterior distribution by drawing random values from it. And that's actually, in a lot of ways, more useful than having the posterior PDF. One, it's doable, so that always helps. But like if you had the choice between a posterior PDF and like 1,000 draws of theta from the posterior distribution, you all would take the draws every time. Because in order to make inferences or like explain your posterior beliefs, all you have to do is summarize a bunch of numbers. So you can go into R and say like, what's the mean of these 1,000 draws of theta? And quickly you'll get back a number. And that's much easier than doing an integral, even if you had the PDF to do the integral with. So having draws is actually better than having a PDF. And we can get draws. So to put that more specifically, under conditions that are incredibly mild, if we have S simulations or draws, and as S gets large, the average of just the sample average of some function G, where G depends on the posterior distribution of theta given Y. So by theta tilde, I mean a draw from the posterior distribution of theta. I've used this notation several times, but I can't remember whether I actually explained it. When I put a tilde on top of something, that means like a draw of that thing from its distribution. So if we just have S draws of theta from its posterior distribution, stick it into any G function we want, evaluate that G function, and take the average of the realizations of the G function. As S gets large, that is going to converge in probability. It actually converges almost surely to the true analytical expectation of the G function, which of course is the integral of the G function multiplied by the posterior PDF integrated over theta, even though that integral on the right is usually going to be intractable. So this thing on the left converges to the thing on the right, even though we can't really write down the thing on the right in any sort of a useful form, but we can obtain the thing on the left. And we control what S is, so we can get sort of arbitrarily close to the expectation of any G function that has an expectation. So just as an example of this, let's say that we have like a circle with a radius of 7/11. The diameter of that circle is 2 times r. The circumference of that is pi times the diameter. if we draw like 10 million values from a gamma distribution whose shape parameter alpha is equal to the circumference here, and whose rate parameter is equal to the diameter, that sample average of that, when we just do mean in R, that's converging to the true mean of this gamma distribution. And the true expectation of this gamma distribution is equal to shape divided by rate. So in this case, it would be, pi times diameter divided by diameter, so just pi. And in fact, that is going to converge to like 2 or 3 decimal places at least to the number pi. So you'll get something like 3.141, when you do that in R. And that's plenty close enough for all sorts of social science or business purposes. So like I was saying, you can substitute having a whole bunch of draws from some distribution, in particular a posterior distribution, for actual sort of analytical mathematical functions that, such as the posterior PDF, that characterize that distribution. And this idea that you can take random draws and the average of them to estimate an expectation is called Monte Carlo integration. So pretty much substituting random numbers for the calculus principle of taking an integral. And this Monte Carlo integration business, it works, and it works even if the draws of theta from the posterior distribution are not independent of each other. In particular, the draw at time s, or the sth draw, is not independent from the draws before and after it. And marginally, it's not independent of the draws even farther forward and farther backward. We do, and we'll talk about this more on Thursday, have to keep in mind that the rate of convergence of this average on the left in terms of its convergence to the expectation of the G function is faster if these draws of theta are independent or close to independent of each other. It's slower if they have a high amount of dependence, but as s goes to infinity, it's going to work either way. So the point of all this is really all we need is a way to obtain. Oh, question.
Just curious about this, they'll stay in the same region.
Yeah. So basically, like the average thing on the left entails getting like s pieces of information, but if like the 100th piece of information tells you something about the 101st piece of information, you really don't have like 101 independent pieces. It's sort of like asking you and your brother, because a lot of the information about your brother is implied by you. But anyway, so all we really need is a way to obtain a large number s draws from the posterior distribution that are not too dependent. And then, we can approximate any G function we want with those draws, and we don't have to actually deal with the posterior PDF. And particularly, we don't have to deal with the denominator piece. All we are going to need to make this work is the numerator. And that's just specifying 2 functions and multiplying them together. Yes?
Why wouldn't the draws be independent in just like a random computer?
So with R gamma, they actually are independent, and that's fine. What we're going to do next, they won't be independent, and that's fine too, as long as they're not too dependent.
So for this to work, we need just the likelihood of the numerator?
No, you need both the prior and the likelihood,
Prior and the likelihood.
but not the denominator. Okay? Good? Okay, so to start with like a simple example, let's say we have a sample space that's discrete and finite, like it has 3 elements to it. And going back to what I said at the beginning, we need some sort of a rule to specify, if we are at one place in omega, how we move to another place in omega. And that rule is sort of encoded with a conditional probability distribution, in this case, a conditional PMF of moving, from any one element of omega to each other element of omega, including the probability of staying in the same place. So to sort of be more concrete about that, let's imagine K is a matrix and whose rows are simplex vectors. So they're non-negative, they add up to 1. They can basically be interpreted as a PMF. And the number of rows and columns of K is equal to the number of elements in omega. And we're going to interpret each cell of K, so K in the ith row and the jth column, as the probability of moving from state I to state J. And state I and state J, I and J are basically elements of omega. So the probability of moving from the ith element of omega to the jth element of omega. And we're going to let this process evolve for an approximately infinite number of moves. So just to be even more concrete about this, let's say we have 3 elements in omega, good, bad, and ugly. And we make a K matrix that's 3 by 3, such that all the elements are positive, and each row sums to 1, which is what I've done here. And we're going to interpret that. So K21 is the probability 0.4 here. And that's the probability of changing if we're in bad now, which is state 2, to good. So the rows are sort of where we are now and the columns are where we might go. But there's a 0.2 probability that if we're in state bad now, we stay bad in the next time. So each of these represents a transition probability through all the states, given where we are now and where we're going, and there's some probability that you stay in the same place. So if we just make like a holder that's like 10 million long, and we start, it doesn't really matter what state we start in, we'll just choose one of those randomly. And here's the important thing. So we loop over, now you can't see it, but this is the important thing. So we loop over all 10 million transitions that we want to do. We sample state, 1 to 3, take a sample of size 1, and the probability is going to be taken from some row of K, depending on what state we're in now. And we're going to use those probabilities to randomly draw where we're going to go in the next iteration. So for the next value of I. And we're going to save that as the current state, and we're going to stuff that in our holder vector in the ith element, and we're going to do that 10 million times. Question? No? I is the index of the loop. So for I equal 1, I equal 2, I equal 3, just states is the vector that we're going to hold all 10 million footprints in. State, singular, without the S on the end, is the state we're in now. And so we're going to draw the new state using, so let's say state is 3 now. We're going to use the third row of K to govern the probabilities for where we go next time. And so that's going to be into state 1 with 0.5, into state 2 with probability 0.3, and stay in state 3 with probability 0.2. And so every time, we could stay in the same state, but there's some possibility of moving. And every time we move, we look in a different row of R, a different row of K, to give us the probabilities to where to go next. So we roll that, 10 million times, and it seems kind of intuitive, although it might not seem like definitively true, that if we just do that for a huge number of iterations, what we're going to get back is a marginal probability mass function on this sample space. So just by specifying this conditional probabilities of like, I'm here now and I'm going to move there with probability something, and I'm going to move there with probability something, and I'm going to move, stay in the same place with probability something. By specifying this whole network of movement probabilities, and moving approximately infinite number of times, where I go is going in the proportions of times that I spend in each of the three states is going to be a probability mass function for that sample space. So that probably doesn't seem like definitively true, but it probably seems plausible. And I can actually sort of show that this approximates something that is equivalent, but doesn't require that you do like 10 million iterations. So a more efficient way of doing the same thing is by taking an arbitrary simplex vector, let's call that P, and then take that as a row vector, multiply it by K to get a new simplex vector. So when you multiply a simplex vector by a transition matrix, you get a new simplex vector. And if we do that over and over and over again, we'll eventually get to the point where the simplex vector is not changing. So you can take this simplex vector, let's call it P, multiply by K, and you get back P. So multiplying the new P, which is the same as the old P, by K again, you're still going to keep getting P. So in that sense, we say P is converged, and we have an example of that here. So this is just creating a random simplex vector. I start with 3 draws from the gamma distribution, and then I divide those 3 draws by the sum of the 3 draws. So now I have a simplex that's going to be distributed Dirichlet. And all I really have to do in this case is like 15 iterations of my loop where I multiply P by K and set that equal to the new P vector. Do that over and over again, but really over and over is just like 15 times. And then P is not going to change anymore. So I can multiply it by K however many times I want. It's not changing. It's sort of in equilibrium. And I don't want to get into details of this, but this is actually the equivalent of taking the first eigenvector of K transpose and then renormalizing it so the elements sum up to 1. So if you take what we had before, which was these 10 million states, and just do a proportion of times that it was in each of the 3 states, good, bad, and ugly, you can see it's like 0.693, 0.146, 14597, etc. This method of multiplying P by K 15 times comes out as something very similar. And this analytic solution, which involves renormalizing the first eigenvector of K transpose, comes out to the same thing. So this thing that we did on the previous slide of like watching this thing move back and forth 10 million times, it's converging to what we have here by renormalizing the first eigenvector of K. So basically what this is saying, the information in K, each row is simplex vector specifying the transition probability of moving from state I to state J. Like embedded in that K matrix is all the information that we need to say what's the marginal probability of being in the good state, the bad state, or the ugly state. We just have to tease it out. And you can do it the sort of brute force way with 10 million transitions, or you can do it with like 15 vector multiplications by a matrix, or you can do it with this eigenvector business. But the point is, those 3 things tell us the same information, namely what's the probability mass function implied by this transition matrix K. And in the discrete case, that's all well and good. We're usually going to do continuous parameters that we're looking for. And so then the question really becomes, can we specify a set of transition probabilities such that the marginal, the PDF or the PMF for the unknown parameters is equal to the posterior distribution that we want. So or at least from the numerator. So, we have our prior distribution, we have our likelihood, we can multiply those together. Is there any like giant K matrix that we can specify such that, the probabilities that we can squeeze out of it are the posterior PDF? If so, then, we're pretty much going to be doing like the first case here of just wind it up and let it go. But if we can sort of align our posterior kernel with some transition rule K, then where it goes constitutes a set of random draws from the conditional distribution of theta given the data. So what we're pretty much going to be doing in the case of a continuous sample space for theta is not like the second and third thing, which give us a pretty quick solution, but rather something much more like the first thing, where we can just sort of let a computer do a whole bunch of transitions for us, and then we'll take those as random draws from the posterior distribution. But we have to have a way of sort of specifying the transition rule such that the probabilities of being in any particular state match up with our posterior kernel that we specify by multiplying a prior PDF by a likelihood function for these data. So yes.
So the transition probabilities are the actual equivalent to the multiplication of posterior with the prior.
If you follow these transition probabilities, you are going to get draws from the posterior distribution you want. So we just have to set it up and watch it go.
Oh,
Yeah.
Each state
So all this K is the probability of moving from here to there, which is not exactly what we want. But if we follow these transition probabilities over and over and over again, the sort of summary of where we've been and the amount of times we're in good state, bad state, ugly state is the same as taking draws from the posterior distribution and then saying what proportion of the time are you in this or that state. And with a lot of complication, most of which we're not going to really get into, that this is also going to work when the posterior distribution has a continuous sample space rather than this one, which is finite, and we can sort of represent it with a finite dimensional matrix. So this sort of transition probabilities and watch it go constitutes random draws from some distribution. And you just need to line things up so that some distribution is the posterior distribution that you want, which can be characterized just with the numerator of Bayes' law. Okay, so how might we do that? The first thing to talk about is a Gibbs sampler. And this is really what put Bayesian approach on the map once people outside of a very narrow subfield of physics figured it out. And this, generalizes to the case where theta is a real number or vector of real numbers. So we can write the posterior PDF, or at least so we can write the posterior PDF for theta given y as a conditional PDF for theta k given all elements of theta except the kth and y. And we can multiply that by a PDF for theta, or all elements of theta except the kth, times y. So this is just the general multiplication rule. Those two things multiplied together constitute the PDF for theta, all of theta, given y. So theta negative k is a vector that contains all elements of theta except for the kth. So what a quote-unquote Gibbs sampler does is it draws randomly from the full conditional distribution. And the full conditional distribution is the distribution whose PDF is this thing here. It's the PDF for theta k given theta negative k and y. So if we know what that PDF is, and we know how to draw from that full conditional distribution for theta k given theta negative k and y, then we can just take a draw of theta k from that distribution and then move on to the next value of k, which is going to be another element of theta. So we can cycle through all values of k, each time drawing from the full conditional distribution. And these full conditional distributions basically give us transition probabilities. So if I know what the full conditional distribution is, let's say it's normal, I have a rule by which I can go from whatever theta k is now to the next realization of that theta k. I'm going to draw from a normal distribution. And then that will be the next state for theta k. And then I'll go on to theta for k plus 1. So that's one way of obtaining draws from this k-dimensional thing, theta given y, if I can just draw from one of them at a time, conditional on all the others. So how might you determine this kth full distribution? So you start with the posterior kernel, the numerator of Bayes' rule. You can actually drop any constants that appear there. And then if we're focusing on theta k, then you can also drop every term from the posterior kernel that does not involve theta k. So just get rid of all the ones that only depend on other values of theta. So now you have your kernel function of the full conditional distribution. And then you, because you know a whole lot of distributions, or you have a computer that can do some pattern recognition stuff for you, hopefully you recognize that kernel as like the kernel of a gamma function, or the kernel of a normal distribution, or the kernel of a beta distribution, or the kernel of chi-squared or something like that. And you're like, well, I know a function in R that I can call to draw from that distribution. And then you just draw from that distribution, and the parameters that go into what you have to specify, like if you're drawing from R norm, like the mean and the standard deviation when you draw from R norm, are going to be dictated by the other elements of theta besides the kth. And so you just draw from R norm if that's the appropriate full conditional distribution, and you move on to the next value of k. So you keep cycling through, k equal 1, k equal 2, all the way up to big K, which is the number of elements in theta. Draw from each element in turn, conditional on all the other ones, and then repeat that like 10 million times. And in the end, you're going to have draws from the posterior distribution, the joint posterior distribution of theta as a whole, conditional on y. So we're not going to actually do that in this class. You do it a lot in the Bayesian class in the stat department. It's an older technique now, but you still see a lot of people using it. And basically, it's sort of the continuous analog of the thing that we did with the 3 states, good, bad, and ugly. These full conditional distributions constitute a transition rule. And all we have to do is draw from the full conditional distribution, and we know where to go next randomly. Just do that over and over and over and over again, and you have draws from the posterior distribution. Okay? So again, we're not really going to do that on homework problems or anything like that. But just as an example of it, let's say we want to draw from a posterior distribution that's bivariate normal. Now, bivariate normal is one of the cases we have already a function in R that can do it for us. But let's suppose we didn't know such a function existed. How could we do it using a Gibbs sampler? And to make this easier, I'm going to say we're drawing from a quote unquote standard bivariate normal. So mean 0, standard deviation 1. And we have some correlation rho that we're going to set to a fixed number like 0.5. So if the joint distribution we're trying to draw from is standard bivariate normal, what are the full conditional distributions? So what's like the conditional distribution of the first thing given the second thing? And what's the conditional distribution of the second thing given the first thing? So to work this out, remember, because we did this in the week on matrix algebra, and you said you understood at the time, that if Z1 and Z2 are independent and standard normal, and we multiply them by this matrix L that's lower triangular and has positive diagonal elements, and shift it over by mu, but mu in this case is 0, we have variables x that are a function of z, and these variables x are multivariate normal. So not necessarily standard normal, and they can be correlated. So a general multivariate normal distribution that we obtain by taking independent standard normals z and multiplying by this L matrix. So that was in the notes if you need to review it. And in this case, the L matrix is going to have 1 in the top left, rho in the bottom left, 0 in the top right, and the square root of 1 minus rho squared in the bottom right. So we're going to multiply that on the right by this vector of z1 and z2. So to just work that out, we have z1 multiplied by 1 plus z2 multiplied by 0. So that's just going to be z1 in the top there. And then the second row, we take z1 and we multiply by rho, and we add to that z2 multiplied by the square root 1 minus rho squared. So that's going to have a multivariate normal distribution. But in the top here, we have the relationship that x1 is equal to z1. And so we can make that substitution to write x2 as a function of x1, because x1 is just another name for z1. And what we have here, so if we take this z1 and we call that x1, which is true, it's just two names for the same thing, we now have a relationship where x2 is equal to rho times x1 plus the square root 1 minus rho squared multiplied by z2. And that has the same form that we've also seen before, where like x is equal to mu plus sigma times z. And we saw in that case, if z is standard normal, then x is going to be general normal with this mean and this standard deviation. So what we've discovered here is that the conditional distribution of x2 given x1 is univariate normal, with mean equal to rho times x1 and standard deviation equal to the square root of 1 minus rho squared. Rho, again, is a correlation, so it's between -1 and 1. The square of it is between 0 and 1, so this square root is a valid operation. Also, just by permuting x1 and x2 around, we find that the conditional distribution of x1 given x2 is also normal with expectation rho times x2 and same standard deviation sigma equals the square root of 1 minus rho squared. So if x1 and x2 are bivariate normal, x1 conditional on x2 is univariate normal with a mean and a standard deviation that we can figure out. So if we wanted to draw from one distribution, one conditional distribution, and then the other conditional distribution, we could do so. And in fact, on the next slide, I have created a movie that shows this. You probably can't, maybe you can see the green lines there, but this is a Gibbs sampler for a bivariate normal distribution. It moves either left or right randomly according to that conditional normal distribution, and then up or down randomly according to the other conditional normal distribution. And you can, let this go for like 30 seconds or whatever. If it went for an infinite amount of time, you would see the draws are going to concentrate according to the PDF of the bivariate normal, whose contour lines are in green here. So we're like at the red point, and then we move either left or right and then up or down according to these univariate but conditional normal distributions of one given the other. So this is an example of how a Gibbs sampler moves. It can really only move at right angles through the space, which is a limitation of it. But it does move through the space, and it's going to have more draws in areas of the joint distribution that have higher density, and less draws like way out here where the density is lower. So that's sort of a movie of how a Gibbs sampler works. And when the code goes up on Courseworks, you can see how to run this yourself. Questions about the basic idea of a Gibbs sampler? It's not so important for this class to understand how to implement one, just the idea of it. Yes, Adam?
Why is on the video remove the right angle disadvantage? I can't any movement decompose into
Yeah, but you have to go in 2 steps. So it's not the most and it's not just 2 steps. Let's say this was 1,000 dimensional. Then you can still only go in right angles, but through 1,000 dimensional space, when sort of the diagonal way would be a more efficient way. Yeah, so just like taxis would be better if they could go like Back to the Future style and cut over from Amsterdam to Broadway, and still go up or down 2 blocks. So in high dimensions, the sort of right angle thing is a bit of a limitation. Okay, so the main limitations of Gibbs sampler, it's only possible when you have the ability to recognize the name of the full conditional distribution. If a distribution has a name, there's probably an algorithm to draw randomly from it, like normal or gamma or chi-squared or something. But if you encounter a full distribution that you don't recognize, or maybe doesn't have a name or an algorithm to draw from it, then what are you going to do? And this has the perverse limitation that it causes people to only specify priors and likelihoods such that they can get these full conditional distributions that have named forms. So they can draw from those distributions easily. So it's sort of a big, but not, it's still only 1 step removed from just specifying like conjugate. And it's pretty much a multi-dimensional analog of conjugacy, where like we can recognize the names of the full conditional distributions. And if we can't recognize the full conditional distributions, then you can't really do a Gibbs sampler. Also, the quality of your estimates that come from the Monte Carlo integration depend on how correlated in the posterior distribution the parameters are. So you can sort of see in this case where the correlation is not 0.5, but like 0.98 or something like that. It can't really move very far because, it can only go up and down, left to right. And, the posterior distribution is so concentrated along this sort of southeast to northwest band. So we can only make like really small steps. And if you can only make really small steps, then the dependence between where I'm at now and where I'm at next is going to be high. And in that circumstance, Monte Carlo integration converges more slowly to the expectation of the G function that you're trying to make inferences about. So with high posterior correlations, and you sort of never know what's going to have a high posterior correlation in a high dimensional problem, because it's not even just bivariate correlation. It's sort of like the dependence of one on everything else. You can get these really small steps and this really high dependence, and consequently very slow convergence to the true expectation. But still, like if you run it for an infinite amount of time, these points that come out, they are draws from the posterior distribution. They're just highly dependent draws. And so that's a limitation as well. The other main form of Monte Carlo, and this is specifically called Markov chain Monte Carlo. The Markov chain business is a particular way of specifying a transition rule that only depends on where you are now. So where you are next only depends on where you are now, and conditional on where you are now, nothing in the past matters for where you go next. So it's just sort of a 1 step back dependent structure. So that's known as a Markov process. And if you specify a Markov process to draw from some probability distribution, That's called Markov chain Monte Carlo, or MCMC. And you can use those draws to do Monte Carlo integration, which is basically substituting an analytical integral for a summary of a bunch of draws from that distribution. So the other main historical way of doing Markov chain Monte Carlo is known as Metropolis Hastings, who were two physicists back around 1950, who were, part of the Manhattan Project, along with the Tellers and the Rosenbluths and people like that. So this is actually something that physicists came up with to, basically tell them a probability distribution for where an electron is. So if you have like basic physics, it's like hard to figure out the position of an electron, because by measuring the position of the electron, it moves it. So they needed a way of getting a probability distribution for where an electron probably is, rather than sort of measuring directly where it is. And so this sort of evolved itself into a statistical thing known as Metropolis Hastings algorithm that involves specifying another probability distribution. So this is sort of a proposal distribution for theta prime, where the prime sort of means the next candidate for theta, conditional on theta, which is sort of the state that you're in right now. So you have some other distribution, and it has PDF Q that's easy to draw from. So you can draw from the distribution whose PDF is Q. Q is typically going to be a multivariate normal. So you draw this candidate for theta prime, from the distribution of Q, and you accept this candidate for the next state with some probability. And this probability is equal to alpha, and alpha is equal to the lesser of 1, and this ratio on the right. So what we have here on the right is the posterior PDF evaluated at the candidate theta, and you took the candidate theta from the distribution whose PDF is Q, divided by the posterior PDF evaluated at the theta that you had previously, or really the theta that we have right now. So that's theta at t minus 1. So we have a ratio here. And we also have the ratio of the Q's, where Q is another PDF. That not only that distribution is easy to draw from, it's easy to evaluate what Q is. So here in the numerator, we have Q, that PDF for the old theta, conditional on the candidate for theta, divided by the Q PDF at the candidate for theta, conditional on the previous value of theta. So this is just 4 numbers, multiply and divide them together, we get another number. If it's bigger than 1, then alpha is simply equal to 1, and we accept theta prime is our new state, our new realization of theta. If this 4-term piece is less than 1, then we're going to accept the candidate of theta with probability equal to whatever number this comes out as. And the reason why this works, you might say, well, okay, if we knew the posterior PDF, we wouldn't have to be doing all this. But you don't actually have to know the posterior PDF. All you have to know is the posterior kernel, because whatever constants there are in the PDF here, it's the same constants in the denominator down there. So whatever those constants are, we don't have to know them because they cancel. And that's really the key to like every hard math problem. The way it gets solved is because somebody figures out how to cancel the crap that they don't know how to figure out. So as long as those constants are finite, then they cancel. And the same thing with the Q, but it's maybe a lesser deal because we can choose Q to be any convenient function. And so you really only need to know the posterior kernel, and you can implement this. And the way it's done, so you calculate alpha, and then you draw U from a standard uniform between 0 and 1, And if alpha is greater than u, then you make the state at time t be equal to the candidate. If u is greater than alpha, then you set the state at time t to be the same as the state at time t minus 1. So you stay in the same place for another iteration of the MCMC algorithm. And then you just go on, take another value of candidate theta from Q and do it all over again. And do that like 10 million times. The resulting thing is going to be draws from the posterior distribution of theta. There's some special cases where like this thing on the right is always 1. In that case, this is known as a specialization called metropolis. So the Hastings part, the Hastings guy figured out that the Q function doesn't have to be symmetric in its arguments, and this still works. There's also a not very useful case where the conditionality doesn't matter. That's known as independent metropolis Hastings, and it's not very common would the Q function have that property. But it makes it easier to do like theoretical analysis of a Markov chain if you can use a Q function that actually doesn't have any dependence. So we're not going to implement this either, but this is a more general way of doing MCMC because you don't have to know anything about full conditional distributions, and you don't have to like recognize full conditional distributions as having named forms like gamma or anything like that. All you have to do is have some PDF Q, and to be able to draw from that distribution to get candidates, and then it's pretty easy to write the steps to decide whether to accept the candidate or not. That's going to have some randomness to it, and so you get random draws from this distribution. And if you use your posterior kernel here as the ratio on the left, then the draws that you get are draws from the distribution whose PDF is F. So this is Metropolis Hastings is a more general thing. Like you can always do it as long as you can write down your posterior kernel. But it has some limitations as well that mostly have to do with how close the proposal distribution that you're drawing from is to the posterior PDF that you're trying to get draws from. So if those like overlap a lot, then Metropolis Hastings can be okay. But if they are like very different distributions, then this is going to be a very inefficient way of getting draws from the posterior distribution. And what I mean by that is alpha will tend to be very small. And so either you have like if alpha is small, then you have a very large chance of staying in the same place again. And you can sort of think, well, if like 3 out of 4 times you do this, you stay in the same place, that's not, you have like very, very high dependence if most of the time you stay in the same place. Like you're exactly equal to where you were before. And you only have like a 25% chance of moving. And even then you tend to not move very far. So you can write this down, you can evaluate it pretty quickly on a computer, but you get draws with like very, 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 very high dependence. And consequently, your Monte Carlo estimates are not very good unless you sort of literally run this for an infinite number of iterations, which isn't physically possible, nor do we have the patience to do it. And so getting a Q function that works well is very hard to do when theta is a high dimensional vector, like even 10, much less 1,000 or 1,000,000 or something like that. In the vast majority of Metropolis Hastings usage, they're doing specifically what is random walk Metropolis Hastings, or using multivariate normal as your distribution for Q, because multivariate normal is like the only distribution pretty much the only distribution that we know how to draw from, like we have an algorithm to draw from it. And so that's, gets your proposals for theta. So specifically, what multivariate normal distribution is this? Well, this is a multivariate normal distribution whose expectation vector is theta, which is the state of theta that we're in now. So we're sort of drawing from a multivariate normal distribution that's centered on where we are now. But if it's a multivariate normal, it has a second parameter, the variance covariance matrix. And what does this variance covariance need to be? Well, you can choose it to be whatever you want. The only one that really works that well is by setting this variance covariance matrix equal to the variance covariance matrix of the maximum likelihood estimator. But if that turns out to be a good choice, then the maximum likelihood sampling distribution is going to be multivariate normal and very close to the posterior distribution, which is also going to be multivariate normal. So really the only case in which this works well, the maximum likelihood estimates are going to be a pretty good substitute for the Bayesian estimates anyway, in which case, like, why go through all this complication? You could just do like maximum likelihood and misinterpret it as Bayesian thing, but it's going to be about the same numbers. So there's not a whole lot of cost there. But bottom line, it's very hard to do this well at all in high dimensions. And the video on the syllabus for Thursday goes into more detail about why this is the case. But Metropolis Hastings and Gibbs sampling, or maybe like a combination of Metropolis Hastings and Gibbs sampling, where like you use Gibbs sampling when you can recognize the full conditional distributions, and you do like a little bit of Metropolis Hastings for those full conditional distributions that you don't recognize. So basically, Metropolis Hastings or Gibbs or some combination is how almost all Bayesian analysis was done from like the early 1990s to 2011 when Stan was released. So there's just a huge literature and a lot of applications of these algorithms, and they're still being used for today by people who haven't heard of Stan yet or something like that. Okay, so we're not going to dwell too much on those, but historically they were very important. All right, so questions?
Data is like just here subscripted. I'm assuming it's like divided into it's divided discrete space, even though it's continuous.
No, it's continuous. So everything in theta is a real number. So there's no discretation.
So when it was like the Gibbs Sampler, we had like k thetas, fixed k thetas.
Right. So it's going to have some length k, 8, 9, a million, whatever. But that's just the number of elements in that vector. The elements themselves are real numbers, almost always. And the Gibbs sampler and the Metropolis Hastings sampler work or can work, whether they're discrete theta or continuous theta.
So how do we get the Q function and like typically in applications?
It's almost always, if you're going to do this, which we're not, but when other people do it, they're almost always going to use multivariate normal as the Q function. The expectation is going to be theta where we are now, and they're going to choose the variance covariance matrix somehow, often by doing like maximum likelihood first, and that gives you like an approximation of the variance covariance matrix, and then do like MCMC after. But yeah, we're not going to do any of that. Okay. All right. So here, what we have, okay, so we have, this is the same bivariate normal that we did before when we were doing Gibbs sampling. So we have x1 on this dimension, we have x2 on that dimension. And then in the vertical dimension, we pretty much have the PDF, except rather than the PDF, it's the logarithm of the PDF. And instead of being the logarithm of the PDF, it's actually -1 times the logarithm. So the actual log PDF is sort of this shape, but flipped over on the Z dimension. But anyway, so we have this shape that is pretty much upside down bivariate normal log PDF. So the ones at the bottom here are areas where there's higher density. And again, X1 and X2 are correlated, like 0.5 or something here. So you can see there's sort of higher density on this kind of diagonal line from, over here to sort of back there. Lower values, because this is upside down, constitute higher values of the bivariate normal density function. Conversely, we have up here these high values, which are actually correspond to low values of the bivariate normal PDF. Because here we have sort of a high value of X2 and a low value of X1, which is unlikely when X1 and X2 are positively correlated 0.5. So if X1 and X2 are highly correlated, it's unlikely you would have an X1 that's -3 and an X2 that's +3. Possible, but very, very unlikely compared to values of X1 and X2 that are more similar to each other. Okay? Does everybody understand this is just an upside down bivariate normal PDF? So you might ask me, why is it upside down? And that is because we can turn this around and we can see spots that I've put on here. So this sort of represents the evolution of how this thing moves in an algorithm like STAN. So say we're at the black dot here, and we sort of kick it in some direction, which we'll not worry so much about, but we kick it and it sort of goes up in the air and it lands on the red spot. And then it just rolls. So I can't get it all on one screen too easily here. So we start at the black, we kick it to the red, and we just let it roll. And so after like a little bit of time, it's rolled to the green. And then you can sort of see after like a little bit more time, it rolls to the dark blue. But it starts to go like up a hill here. So the reason why this is upside down is so that it corresponds more directly to your intuition for how gravity works, which I assume you have some intuition for how gravity works. If I put the bivariate normal right side up, then you have to think in terms of anti-gravity. And that doesn't happen on Earth. So, okay, you kick it from the black to the red, it rolls to the green, rolls to the dark blue, but it's starting to roll like up a hill here. So it, kind of turns around, rolls to the light blue, and then it starts going back to the left, to the purple, and then to the yellow. And it's sort of hard to see here, but right next to the yellow, there's gray, which is where it goes next. And you might say, well, the gray is in the wrong place. It should have gone like farther. So what actually happened, it did go farther, but it started, going up the hill to the left. And then it turned around and rolled back down toward the yellow. So that's why the yellow and the gray are so close together. It went farther up the hill and then came back down almost all the way to where the yellow was. Okay. So, I mean, if I turn this maybe more. So now you're looking like straight down on it. Still kind of hard to see. You can play around with this on your own computer. But you can sort of see like, okay, this corresponds to like physics, more or less. Exception being there's no friction on this surface, which you may have like not a whole lot of intuition about frictionless surfaces. But mathematically, this is actually, I mean, it's hard for me and it'd probably be hard for you. But for somebody who like majored in physics and you say like you don't have to worry about friction or wind or like earthquakes or anything like that, like how would this thing go if it had like this amount of momentum in this direction? And like mathematically, that's figure outable. Like if we can get a rocket ship to the moon, we could probably figure out like how to go from red to green in a physically like appropriate way. It's not like for a college physics major, it's not that hard to figure out like how far you would go in this amount of time if you had this amount of momentum going in this direction with this amount of incline. Now, I'm not going to ask you to figure out any of that, but you probably have a friend who would be like, yeah, I could do that. Enemy, I don't know. Frenemy. It's not that hard. And this is sort of the intuition of how Hamiltonian Markov chain Monte Carlo, and Stan is a variation of that, works. You sort of randomly kick the thing, wherever it is now in some direction, and you let it roll, and the incline here is characterized by your posterior kernel, the right-hand side in the numerator of Bayes' rule, the distribution you're trying to draw from. That governs the shape of this. And then sort of physics governs how it moves in this space. So when, Hamiltonian Markov chain Monte Carlo does, you're in some state theta now. You randomly like get kicked in some direction. You roll for a little while. At some point, after you roll for a little while, so because it's a frictionless surface, you could like roll forever. But at some point, we just say like cut, and then we see where it's rolled to. And then we're gonna, among the footprints of where it was, so we're sort of discretizing time here instead of doing a continuous thing. But sort of in discrete time, you have these footprints of where you rolled to, which correspond to the dots here that are different colors. And we're just gonna take one of those footprints with probability proportional to the posterior kernel. So places that have a high posterior kernel, they're gonna be low when it's upside down. So the ones in the lower area, they're gonna have higher probability of being selected than the ones like the yellow or the gray or the blues over here that have lower values of a posterior kernel. And so if we select the footprint with probability proportional to the posterior kernel, then the draws that we obtain in this process are going to be draws from the posterior distribution. And sort of the thing with Stan is, because it's doing this sort of physics stuff, where you start out, like where you were last time, the black dot, is not so important. Like the dependence is a lot lower because it has more to do with like where you go depends more on the shape of the posterior distribution than where you started. And also like how much momentum and stuff that you get. So that's a little bit of an intuition for what's known as Hamiltonian Monte Carlo. So we have theta, it's a parameter of length k, and we're going to also introduce this other parameter phi that is also of length k, and we're going to call phi the momentum vector. So really what we're trying to do here is draw from the posterior distribution of theta and phi conditional on y. And so if we write out that posterior kernel, it's going to be your prior for phi, which is the momentum, multiplied by an independent prior for theta. So phi and theta have no dependence, and so we can write their joint PDF as a product, multiplied by the likelihood. But the likelihood function only depends on theta and y, but not phi. Consequently, the posterior part for phi is going to be the same as the prior. The data has no information about phi. And that's because phi is really more of a catalyst. And so if the likelihood doesn't depend on phi, then the posterior of phi is going to be the same as the prior for phi. We're not going to update our beliefs about phi at all if the data are not a function of phi. So we're sort of free to choose the prior for phi to be whatever we want. And we're going to choose it to be multivariate normal, in which case the logarithm of that is going to sort of correspond in physics terms to kinetic energy. So the momentum by which theta is sort of pushed through this upside down posterior density phase. And so at each iteration of the Markov chain Monte Carlo, we're going to draw a realization of momentum from a multivariate normal distribution. And that's a signed quantity, and it's going to have some magnitude. So the positives and negatives in phi determine what direction we're moving in this multidimensional space. And the magnitude is the force, the momentum. So how rapidly we move, in the positive direction or the negative direction for any of these things. And this momentum is going to push theta through the multi-dimensional space. So here, each point is sort of a footprint of theta, and it's being pushed, from black to red to green to blue, etc., based on the initial realization of momentum that we drew for phi from a multivariate normal distribution. And so theta is the position vector in physics terms. And by physics terms, I specifically mean Hamiltonian physics, which was invented in the 1800s to describe how things move in a three-dimensional space. But it also applies to a multi-dimensional space. And this multi-dimensional space is going to have a topology to it. And that topology is defined by, in physics terms, what we call potential energy. But in sort of statistics terms, it's just the negative of the numerator of Bayes' law, but in log units. So the negative of the logarithm of the numerator of Bayes' law. And we can specify these two functions for the prior and for the log likelihood. And because Hamiltonian physics assumes that there's no friction, it has the mathematical property that changes in kinetic energy have to be zero sum with changes in potential energy. So consequently, the Hamiltonian, which is the sum of kinetic energy and potential energy, it's, if you move the theta, you have to move the momentum in a corresponding way, so it stays constant. And this basically gives us a system of ordinary differential equations, so we can set derivatives equal to zero, solve, albeit numerically, for where sort of the next position of theta is. And if theta moves to this position, how its momentum has to change to keep the Hamiltonian system in balance. And this process of sort of, you randomly get momentum, you change the position, you start to go up hills and stuff, it changes your momentum, that governs where you move next. Just keep doing this over and over again, solving these physics equations for the new position and the new momentum gives us footprints. And once we have footprints, we can draw from them with probability proportional to the posterior kernel. And this is how Stan works and how Hamiltonian Monte Carlo works to get draws from a posterior distribution that we define by our choice of prior and likelihood. So we'll talk more about that on Thursday. Definitely watch Mike Betancourt's video. There's also a relatively readable article, even ecologists can understand it, on how Stan works. That's also on the syllabus for Thursday. In addition to the stuff from Kushke, which sort of describes Stan, but sort of describes Stan a few years ago and doesn't exactly have the right explanation in the first place. But it conveys some intuition as to how this all works. Okay, so I'll see you all Thursday.
So, why are we taking the knob there?